Good evening to Doctor. I am Hui representing Group 6. So in this video, I will present Part A Task 3, which focus on proportional controller design for third order control system. So the objective of this task is to determine the proportional gain K that achieve approximately 20% of overshoot using three different design methods, which is the first one, try and error method, try and error simulation. Second one, the analytical approximation, and also the third one, rule Rotter's method. So uh, the plan considered in task 3 is a third order system, which is GS is equal to 1 over S plus 1 times S plus 3 times S plus flat. So a unity negative feedback configuration with a proportional controller is used. So due to higher order nature of system, so different design method may produce different type of result. So now we are going to show the first method, try and error method simulation. So this is a code we are using. And then after we put inside the MATLAB and try to run, so because the process is kind of long when we wait for it to be running, so I make it run first, and then this is the result coming out, and also the graph. So in method 1, a range of proportional gain value is tested using the MATLAB simulation here. So the overshoot is calculated using the step info command, and also the gain is produced overshoot close to 20% right here. And also after we run the code, here is the figures that are being generated. So firstly, it shows the overshoot, whereas the approximate uh, proportional gain K. And also here, the step response, and also the final step response. So Mm, using this method, the selected gain result in the overshoot approximation of 17.04%, which is reasonably close to the design target. So in this case, if we want to see the peak response, rise time, settling time, transient time, and or steady state, so we just right click and then put in the characteristic, and it will show on the graph. And then just like being mentioned just now, it shows the overshoot or approximate to 17%, so which is reasonably close to the design target. So this is the method 1. For method 2, analytical method. So in this method 2, the system is approximated as the second order system using the dominant pole assumption. The damping ratio corresponding to 20% overshoot is firstly being calculated using the standard overshoot equation. And then the coefficient matching is then being used to computate the proportional gain analytically. So as we shown inside this MATLAB, so as usual, I run the code first. Then this is the result coming out. So it shows the overshoot is 45.05%. And also here is the cursor pose. And then let's look at the graph. So here, after I put the, here it shows the overshoot is equal to 45.1%. So this analytical method result in the overshoot of approximately 45%, which deviates significantly from the target. So why does it happen? So this happens because the plant is third order, and the second order approximation doesn't accurately represent the full system dynamic. So the overshoot should be varying very differently. So it does very big difference. So this is for the method 2. In method 3, the root locus of the open loop system is being plotted. So as we show inside the graph, so this is the outcome being plotted by the MATLAB. So a constant damping ratio line corresponding to 20% of overshoot is overlaid using the script command inside the MATLAB. And the proportional gain selected at the intersection, here is the intersection of the root locus and also the damping ratio line. The root locus and also the damping ratio line. So we select the intersection point, we click, and it will come out with the graph of unit step response with selected gain k equal to 31.534. After we click this, we select the characteristic peak time response, peak response, and then we observe. So the overshoot is 18.2%. So it's very close to the design target. So the selected dominant pose accurately reflects the system behavior. So that's all for method 3.
The result demonstrates that for high-order system, analytical second order approximation may lead to inaccuracy prediction. Stimulation on based and graphical methods such as trial and error and root locus are more reliable as they consistent the full system dynamic. The root locus method also provide variable insight into stability and force movement. In conclusion, task 3 highlight the importance of selecting appropriate controller design method based on the system order, where analytical methods are useful for theoretical understanding. The root locus method provides the best balance between accuracy and insight for high-order systems.